So the first thing I want to talk about I want to talk about two things today. I want to talk about the solid angle and the neutron flux. Let's begin our discussion with the solid angle. And to begin our discussion about the solid angle, let's talk about first the unit circle of radius equal to 1. Now, if we draw our originating ray and our terminating ray here, the angle between these, the angle subtended, is going to be theta radians. And it's going to be some sort of fraction of 2 pi. Well, it could be more, but it can always be normalized to some sort of fraction of 2 pi because there's 2 pi radians in a unit circle. If we were to extend this concept to 3 dimensions, we have the 3-dimensional analog of the unit circle is the unit sphere, with radius equal to 1, and it has the surface area of 4 pi, and the analog unit of radian is sterradian, SR. And if we were to subtend out an area, just like we subtend out a length on the unit circle, we have some sort of fraction over 4 pi sterradians. So the solid angle is the amount of area subtended on the unit sphere. And one sort of application of this is like if we have a point detector, and we have some sort of radiation emitting, let's say this is a cylinder. What is the solid angle subtended by the cylinder on this point detector? To do that, we would draw an imaginary sphere, unit sphere, around our point detector, and we would take each vertice and project it onto the unit sphere. We try and intersect it with here. The point and intersection of the sphere and the ray is where it matches up with the where we draw our subtension from. So maybe we have like another thing like that, and it subtends. It casts a shadow of some sort of shape on the unit sphere, and it has X sterradians subtended on the point by the object. So that's solid angle. The other concept I want to cover today, and you'll see the solid angle all the time in reactor physics, and I haven't really found many good textbooks on the subject, so that's why I bring it up. It seems to be something that a lot of physicists just know, and then you ask them, or you try and figure out, where they got it from, and I could never figure out, where they learned this thing from. There's not many good references on the internet, best I can tell. At any rate, the other thing I wanted to talk about is flux, or the neutron flux, and it's denoted this a phi or a phi if you prefer, and it is a function of position, or state space is position, energy, direction, or solid angle, and time. Optionally, it could be invariant with time if it's steady state. And let me give you an interpretation. And its units are, it's a probability density function. So its units are 1 over centimeter cubed second MeV, or energy, and then sterradians. When sterradians is really an imaginary unit, so it's not even sterradians. And that's only sterradians if this is expressed in terms of solid angle. At any rate, let me give you the interpretation before I give you a definition. So it's interpreted is if we have our unit cuboidal volume, and we have some neutrons flying around in it, so what is the total path length that those neutrons trace out in that 1 centimeter cube volume in 1 second, given that position in energy space and that position in direction space? It's total path length. And so we can write this phi of r e, and I'll just omit this for later on, t equals the magnitude of the velocity vector, so our velocity, times the neutron density, PDF, R E omega t. I might just simplify this notation a bit and say the state space is implicit phi of v times the neutron density, velocity times the neutron density. And you can kind of get this interpretation because, as you know, you can multiply any sort of value by 1 and it remains the same. So if we multiply this velocity times 1 second, we get a distance traveled in 1 second. So that's total path length times the number of neutrons traveling that path length in 1 second. So n times path length is maybe a better interpretation would be the rate of path length generation by those neutrons in that state space. The rate of, I like that definition better, path length generation of all neutrons, and I'm using the terminology here, at, meaning at that position in the state space of the neutrons, at, I like this much better, R E omega t. So that's the, like this, interpretation for flux. Okay? And sometimes you hear this referred to as the angular flux. When it's an argument of omega here, because it's the flux traveling at that angle, so angular flux. All right, so that's sort of the definition, and let's go over how you can sort of grab this a bit. We can have flux as a position of energy. We call this the energy dependent flux. The energy dependent flux, we'll write phi as a function of position, and we have phi is a function of position and energy, and what this is the integral over all angles of phi of our angular flux, R E omega, and I'm just omitting the t variable here. So the steady state angular flux. And then we just have the what's colloquially called the neutron flux. And the neutron flux is just the denoted phi as a function of position. So our cube or whatever is at some position vector r. And that's just the integral over all energies of our energy dependent flux. That's our neutron flux. There's a special case I want to touch on. And that's in the case of isotropic angular flux. So isotropic, iso meaning one, and or unity, and tropic meaning direction. So this is maybe iso means more uniform. I don't really know the etymology, but isotropic means that it's invariant with direction, and what we can write is the angular flux phi of r e omega, the steady state, omitting time. The steady state angular flux, this term here, is equal to the energy dependent flux phi of r e over 4 pi divided by 4 pi. So the energy dependent flux at any sort of direction is just 1 over 4 pi of the energy dependent flux, but only in the isotropic case. Okay, so that's the isotropic angular flux. And the last thing I wanted to cover is you can also have some special energy groups. We can have we've already gone over the total neutron flux, phi of r, which just equals the integration over from 0 to infinity of the energy dependent flux. This is the total neutron flux. And then we have the thermal flux. And the thermal flux is just going to be we denote this as phi sub th of r. This is just equal from 0 to what we call the thermal energy, E sub th, of the energy dependent flux. And what the thermal flux is the neutron flux. It's interpreted to be the neutron flux at thermal equilibrium with its surroundings. And we can get this from what we call the Boltzmann constant. The rule of thumb I've heard is that the thermal energy is approximately equal, and I'm not sure where I'm getting this from. I think it's Lamarche. 5 times Boltzmann's constant times the temperature of the medium. And you might recall from your statistical mechanics course, if you've ever taken one, that a collection of particles in thermal equilibrium with its surroundings undertakes a Maxwellian distribution. So the thermal neutron flux is when the neutrons themselves are in thermal equilibrium with the surroundings. And this is important because the cross sections, we'll get into this later, the cross sections change as a function of temperature significantly with thermal neutron fluxes, because what can happen is the atoms, as they're sort of vibrating around in their surroundings, and you have a neutron flux superposition with that, and it's moving around at relatively the same velocity as the vibrations of the constituent matter which the neutrons are within. What can happen is upscattering can happen, wherein the neutrons get hit by a vibrating molecule and energy gets imparted up to them rather than just being scattered down. But we'll get into that later. But just know that the thermal neutron flux is the integral of the energy-dependent flux between 0 and the thermal energy being 5 kT. I've also heard this, if I recall correctly, and I could be wrong, of 0.025 eV, if that's correct. I'm not too sure, so I think stick with this, or better yet, just look it up. And then we have what's called the fast flux. That's the phi sub f of r, and that just equals from the thermal energy back up here to infinity of phi of r, our energy dependent flux, dE. So we're taking our spectrum and just taking the upper part of it. So those are the two-group approximation. In general, we can have an arbitrary number of energy groups. So we can have something called spectrum energy here, and neutron density here, and our neutron spectrum will look something like this. We can break this out into a number of different groups. And we use the convention, I call it the 0 is fastest convention. I've seen this in the marsh, where the highest energy group, or energy at infinity, is 0, and then we have the first energy group, second energy group, third energy group. If you haven't seen this before, this is spectrum. A spectrum just being a plot of something against energy, and the lowest one being the fifth energy group. And we call this group 1, group 2. Let's say this is group 3, group 4, group 5. In fact, it's probably, just to avoid confusing you guys, just erase this. So these are the energy groups, and what we say the Gth group flux. This is equal to, we denote this as phi sub g equals the integral of the Gth group energy and the G minus 1 group energy, your energy dependent flux, R. That should be a function of R, but I don't have room to write it. E D E. So that's a Gth group energy flux. And there's some standards for group structures, and this is a whole active field of study. For example, we have the WIMS, if I recall correctly, the WIMS group structure, which is a 61 group structure, and it just discretizes the groupings, so it makes the problems a bit easier to work with. But for most undergraduate and even graduate level problems, we'll just be doing the 2 group flux of fast and thermal neutron velocities. So that's neutron flux and some information about the energies. Next time we'll be looking at the neutron current.